Hello everyone, welcome to the official YouTube channel of KPRIET EEE. In this video, I am going to explain about the basics of 8085 microprocessor, including architecture, programming and interfacing. What is a microprocessor? Microprocessor is nothing but a single chip CPU. That is, it is a CPU which is integrated on a single silicon chip. We can also call it as the CPU of your computer. Before seeing about the 8085 microprocessor, let us see the evolution of processors. The first manufactured processor was 4004, which was a 4-bit processor. Then 8008 and 8085 processors, which are 8-bit processors. Then came 8086, a 16-bit processor. Then Motorola M68030 and Intel Pentium 32-bit processors, and nowadays we use i3, i5 and i7, which are 64-bit processors. This is about the evolution of microprocessors. Now let us go in depth into 8085 microprocessor. First, let us see the features of 8085 microprocessor. This 8085 microprocessor is an 8-bit microprocessor because the size of the data bus is 8-bit. The size of the address bus of 8085 microprocessor is 16-bit. With this 16-bit, it can address up to 64 kilobytes of memory. It has a 16-bit program counter and 16-bit stack pointers. It also has 7 8-bit registers, namely A, B, C, D, E, H and L. These B, C, D, E, H, L can be combined to form 16-bit registers also. This microprocessor requires plus 5 volt supply and it operates at 3 MHz frequency. 8085 processor is a 40-pin IC with von Neumann architecture. Now, coming to the pin configuration of 8085. As I told you already, 8085 processor has 40 pins. The pin diagram is shown here with 20 pins on each side. Now let us see about this pin configuration and each pin in detail. The first two pins are X1 and X2 and these are called crystal oscillator pins. That is, a crystal oscillator is connected in between this X1 and X2, which generates 6 MHz of frequency, which is internally divided by 2 to create 3 MHz operating frequency for 8085 microprocessor. This 3 MHz frequency can be taken out through the clock out pin of the processor to synchronize with the peripheral devices. Hence, the operating frequency of 8085 microprocessor is 3 MHz. Then, coming to the reset pins of 8085 processor. To reset the processor, we use reset in bar pin. Reset in bar is an active low signal. Active low signal is nothing but the signal which is activated by giving 0. So this reset in bar pin, it is used to reset the microprocessor, which can be done by the programmer. And the other reset pin is reset out pin. It is an output pin which is an active high signal. Active high signal is nothing but the signal which is activated by giving 1. So this reset out pin is used to reset the peripheral devices, and this is done by the microprocessor. The next two pins are serial communication pins, which are used for serial communication. Normally, the 8085 processor performs parallel communication, but whenever there is a need for serial communication, 8085 processor makes use of these pins. There are two serial input-output pins, namely SID and SOD. First, let us see about SID. SID is nothing but serial input data. That is, the data is taken into the microprocessor through this pin bit by bit, and it stores the bit at 8th position of the accumulator. The RIM instruction is used to perform serial input data. The other serial communication pin is SOD, which is nothing but serial output data. This serial output data pin is used to transfer the data from microprocessor to the peripheral device serially, that is bit by bit. It takes the bit from the 8th position of the accumulator. SIM instruction is used to do this operation, that is transferring the data from processor to the external device. Then coming to the interrupt pins of 8085 microprocessor. Interrupt is nothing but a disturbance made by the peripheral device to make the microprocessor to perform a specific task. So there are 5 hardware interrupts in 8085, namely trap, RST 7.5, RST 6.5, RST 5.5 and INTR. So these are the 5 hardware interrupts, out of which trap has the highest priority, followed by RST 7.5, 6.5, 5.5 and INTR has the lowest priority. And there is one more interrupt pin which is not an hardware interrupt, but it is the interrupt acknowledge pin. That is, whenever the processor receives an interrupt through the hardware pins, it will send one interrupt acknowledge signal to the corresponding peripheral device. It is an active low signal and an outgoing signal. So whenever this INTA bar pin goes low, it indicates that the processor has sent an acknowledgement signal to the corresponding peripheral device. Now let us see the address and data pins of 8085 microprocessor. As we have seen already, the size of the data bus is 8-bit and the size of the address bus is 16-bit. So the data pins are named as D0 to D7 and the address bus is named as A0 to A7. The data bus is used to transfer the data between microprocessor and memory and also between microprocessor and IO devices. This address bus is used to carry the address signals and it selects any one of the memory from the 64 kilobyte locations. As we have 8 data pins and 16 address pins, the lower order address pins, that is A0 to A7, is multiplexed with the data pins D0 to D7 and they are named as AD0 to AD7. It serves for dual purpose, that is for transmitting lower order address as well as for transmitting the data. So this depends upon the ALE pin, that is during the first cycle it will act as address bus and for the other cycles it will act as data bus. The higher order address pins are kept separately as A8 to A15 and they are unidirectional pins. So these pins will carry the higher order address. The address will be always sent from microprocessor to the memory. So this address pin will go to high impedance state during hold and reset mode. Now coming to the timing and control signals. There are many timing and control signals which controls the operation of microprocessor. Some of them are ALE, S0, S1, IO by M bar, read bar, write bar, ready, hold acknowledge, VSS and VCC. Let us see about these pins in detail now. The first pin used for controlling the microprocessor is ALE, address latch enable. The function of this ALE pin is used to demultiplex the address bar data bus during microprocessor operations. That is, if ALE is equal to 1, the AD0 to AD7 bus will act as address bus, and if ALE is equal to 0, this AD0 to AD7 bus will act as data bus. So the function of the ALE is to decide whether the AD0 to AD7 pin should act as address bus or data bus. Next comes the status pins of 8085 processor. These are called status pins because it gives the current status of the operation of 8085. S0 and S1 shows whether the microprocessor is doing write operation or read operation, or whether it is fetching the opcode, or whether it is in halt state, that is, it is not doing any operation. So when S0 and S1 is equal to 0, 0, it means the processor is in halt. If S0, S1 is equal to 0, 1, then it means the processor is doing write operation. And if S0, S1 is equal to 1, 0, then it means the processor is doing read operation. And when it is equal to 1, 1, it means the processor is fetching the opcode from the memory. The next pin is the IO by M bar pin. This pin is used to indicate whether the processor is communicating with IO device or the processor is communicating with memory. So in the name itself we can identify IO is an active high signal because there is no bar on the top, and memory is the active low signal. So when IO by M bar is equal to 0, it means that the processor is communicating with memory, and if IO by M bar is equal to 1, then it means the processor is communicating with IO devices. So with the help of IO by M bar pin, S0 and S1 pins, we can easily identify the status of the bus. If IO by M bar is equal to 0, we know the processor is communicating with memory. So when IO by M bar is equal to 0 and S0 is equal to 1 and S1 is equal to 1, then it means the processor is performing opcode fetch operation. And when IO by M bar is equal to 0 and S0, S1 is 1, 0, then it means the processor is reading the data from memory. And if IO by M bar is equal to 0 and S0, S1 is equal to 0, 1, it means that the processor is writing a data into the memory. Now if IO by M bar is equal to 1, then it means the processor is performing IO operation. So IO by M bar is equal to 1, S0, S1, 1, 0 combination indicates that the processor is reading data from the IO device. And if IO by M bar is equal to 1 and S0, S1 is equal to 0, 1, it means the processor is performing write operation with IO device. And if all are 1, then it means the processor is performing interrupt acknowledge. And if S0, S1 is equal to 0, 0, and if IO by M bar goes to high impedance state, then it means that the processor is not doing any operation and it is in halt state. Then coming to read bar pin, this read bar pin is an output pin which is an active low pin, that is, it can be enabled by giving a 0 to the corresponding pin. This read bar pin is used to perform read operation, that is, whenever this read bar pin is low, the microprocessor will perform read operation either with memory or with the IO device. And similarly, there is one write bar pin. It is also an output pin and it is also an active low signal. This write bar pin is used to perform write operation. Whenever this write bar pin is low, it means the processor is performing write operation either with memory or with the peripheral devices. And next one is ready pin. It is an input pin. This pin is used to synchronize the peripheral devices with the microprocessor. Normally, the processor speed will be very high when compared to the IO devices. So, when any slow peripheral device is interfaced with the microprocessor, then the processor will go to wait state until the peripheral devices become ready. So whenever the peripheral device is ready, it will send a ready signal through this ready pin of the processor, so that the microprocessor leaves the wait state and services the interrupt device. Next comes the DMA pins of processor. DMA is nothing but direct memory access. Normally, the data from the I/O device will be transferred to memory only through the microprocessor. That is, from the I/O device to the processor and then to the memory. Similarly, the return operation will be from memory to the processor and to the I/O device. So, this is normal operation. Direct memory access is nothing but without sending the data to processor, the I/O device will directly send the data to memory. So, this is called as direct memory access, that is accessing the memory without sending the data to the processor. This is called as direct memory access. For this direct memory access, two pins are used, hold and hold acknowledge. This hold pin is used by the external device to request the microprocessor for DMA transfer. A high signal on this pin will indicate the processor that there is an I/O device which requests DMA transfer. Few DMA controllers are 8257 and 8237. Hold acknowledge pin is used by the processor to acknowledge the I/O device which requests DMA transfer. So, whenever the I/O device is in need of DMA transfer, it will send a signal to the processor through hold pin. So, after receiving the hold signal, the processor will send one acknowledgement signal through hold acknowledge pin that it has received the hold signal, and it will go to high impedance state, that is, it will be cut off from external environment, so that the I/O device can directly do data transfer with the memory. The last two pins are power supply pins, VSS and VCC. As we already know, 8085 processor requires plus 5 volt power supply for its operation. This plus 5 volt power supply is given to the processor through VCC pin, and this VSS pin is grounded. So, that is all about the pin configuration of 8085. As we know, 8085 is a 40 pin IC, and out of those 40 pins, 2 crystal oscillator pins X1 and X2, 2 reset pins, reset out and reset in bar, 2 serial communication pins SOD and SID, then hardware pin interrupt pins, trap RST 7.5, 6.5, 5.5 INTR and 1 interrupt acknowledge pin, then multiplexed address bar data pins AD0 to AD7, then higher order address pins A8 to A15, then bus status pins IO by M bar S1, S0, then read bar and write bar pins used for read and write operation, then ALE pin which decides whether these AD0 to AD7 should act as address pins or data pins, then ready pin which is used to synchronize with the slow peripheral devices, and DMA transfer pins hold and hold acknowledge, then finally power supply pins VCC and VSS. So, that is all about the pin configuration of 8085 microprocessor. Architecture of 8085 microprocessor. So, the study of architecture is nothing but the study of internal building blocks of 8085 processor. So, this 8085 architecture includes arithmetic logic unit, register array, instruction registers, instruction decoders, timing and control units, interrupt control unit, then serial IO control unit, then address and address bar data buffers. So, now let us see about these blocks in detail. This is the internal architecture or the functional block diagram of 8085 microprocessor. So, in this diagram we can see accumulator, then arithmetic logic unit and a temporary register, a flag register and an instruction register, an instruction decoder and a machine cycle decoder, then interrupt control unit, serial IO control unit and an array of register which includes WZ, BC, DE and HL registers along with stack pointer, program counter, an increment decrement address latch, and there is one timing and control unit which has all the control signals and address bar data buffers. Let us see about these blocks one by one in detail. The first and very important block of 8085 microprocessor is arithmetic and logic unit. It is also called as the heart of the microprocessor, and it performs all arithmetic and logical operations. The arithmetic operations include addition, subtraction, increment and decrement, and the logical operations include AND, OR, XOR, compare and shift. In microprocessor, that is in 8085 microprocessor, there is no specific multiplication and division operation, but the multiplication is done by repeated addition and the division is done by repeated subtraction. Then coming to register array, this register array includes accumulator, temporary register, flag register, general purpose registers B, C, D, E, H and L, a program counter, a stack pointer and an increment decrement address latch. All these come under register array. An accumulator is also called as A register. This accumulator is an 8-bit register and it is used during all ALU operations. So during ALU operation, one data is kept in the accumulator and the result of the ALU operation is also again stored in the accumulator only. Then temporary registers. So these temporary registers are also 8-bit registers, and there are 3 temporary registers in 8085 microprocessor. One is temp, which is kept near accumulator, and 2 8-bit registers W and Z, they are kept near BC register pairs. These registers cannot be programmed by the programmer and they are used only during ALU operations. Next comes the flag register. Flag register is also an 8-bit register and it has 5 flags: sign flag, zero flag, auxiliary carry flag and parity flag. The diagram shows the details of the flags. The D0 pin is used as carry flag. That is, if carry flag is equal to 1, it means that a carry is being generated during any arithmetic operation. If carry pin is equal to 0, then it means no carry is generated. D1 pin is not used. Then D2 is used for parity. So if P is equal to 1, it means that the result of any arithmetic or logical operation has even parity, and if P is equal to 0, then it has odd parity. Then D3 pin is also don't care pin. Then D4 is used for auxiliary carry. Auxiliary carry is nothing but the carry generated from the lower nibble. So if auxiliary carry is generated, then AC will be equal to 1, and if it is not generated, then AC will be equal to 0. Then D5th bit is also don't care bit. Then D6 is used as zero flag. If the result of any ALU operation is 0, then zero flag will be set to 1, and if it is not 0, the zero flag will be reset to 0. Then the D7th bit, it is used as sign flag. If the result is positive, then sign flag will be equal to 0, and if the result is negative, then the sign flag will be equal to 1. So there are 5 flags in 8085: sign flag, zero flag, auxiliary carry flag and parity flag. Then comes the general purpose registers of 8085. There are 6 general purpose registers: B, C, D, E, H and L. All these 6 registers are 8-bit registers, but they can also be combined as BC, DE and HL register pairs to be used as 16-bit registers. Then program counter. Program counter is a 16-bit register. This program counter is used to hold the address of next instruction to be executed. Next is a stack pointer. Stack pointer is also a 16-bit register. This stack pointer is used to hold the topmost address of the stack. Stack is nothing but a sequence of RAM memory location defined by the user to save the content of the register temporarily during the execution of the program. So 8085 processor uses last in first out stack. The last register in the register array is the increment bar decrement address latch. It is a 16-bit register. This register is used to increment the program counter and decrement the stack pointer, because whenever the data in the program counter is taken, it automatically increments by 1, and whenever the data in the stack pointer is taken, it automatically decrements by 1. So this increment bar decrement address latch is used to increment the program counter and decrement the stack pointer respectively. So the next block is the instruction register and decoder. The instruction register, it is used to hold the next instruction to be executed by the processor. It takes the opcode from the memory and holds it in the location. The instruction decoder, it decodes the hexadecimal codes into binary codes, because the processor can identify only the binary codes. So the hexadecimal codes which is programmed by the user is being converted to machine level codes, that is binary codes. This timing and control unit of the processor synchronizes all the microprocessor operations with the clock. So the function of this timing and control unit is to generate necessary signals used for communication between processor and peripheral devices. Few signals of timing and control unit are X1, X2, clock out, ready, read bar, write bar, ALE, and the bus status pins S0, S1, IO by M bar, then DMA transfer pins, hold and hold acknowledge, then reset pins, reset in bar and reset out bar. So this timing and control unit receives the details from the instruction decoder and generates the signal accordingly. The next one is the interrupt control unit of 8085 processor. This interrupt control unit is used to manage the hardware interrupts of 8085. As we already know, there are 5 hardware interrupts in 8085, namely trap, RST 7.5, RST 6.5, RST 5.5 and INTR. So these 5 hardware pins are managed by the interrupt control unit. This interrupt control unit checks the priority of the interrupts, and also it is used to send the interrupt acknowledge to the peripheral device. The next block is the serial IO control unit, which is used to control the serial communication of 8085 microprocessor. It has 2 pins, SOD and SID, serial output data and serial input data. So this unit controls the serial reception and serial transmission of bits one by one. Whenever the processor needs serial communication, this serial IO control unit will use SID and SOD pins to take the data bit by bit serially inside, and as well as to send the data bit by bit serially outside. And the last 2 blocks of 8085 microprocessor are address buffer and address bar data buffer. This address buffer is used to hold the higher order address pins. that is A8 to A15, and this address bar data buffer is used to hold the lower order address and data pins, that is A0 to A7 and D0 to D7, which are multiplexed to form AD0 to AD7. This is about the architecture of 8085 microprocessor, which comprises of accumulator, arithmetic logic unit, flag register, interrupt control unit, serial IO control unit, instruction register, instruction decoder, and an array of registers which contains temporary registers B, C, D, E, H, L, general purpose registers, stack pointer, program counter, increment bar decrement address latch, then timing and control unit, and address bar data buffers. Now, as we have seen the architecture of microprocessor, let us see the interrupts of processor in detail. What is an interrupt? Interrupt literally means disturbance. So, interrupts are the signals generated by the external devices in order to request the microprocessor to perform a specific task. The interrupt signals will be sent by the external device whenever they are in need of the service of the microprocessor. So, when the microprocessor receives the interrupt signal, it will send one interrupt acknowledge to the corresponding device, and it will check the priority of the interrupt. If the priority is higher, the microprocessor will suspend its current operation and it will go to service the interrupt. But if the priority is lower, then the microprocessor will complete its present operation and then it will go and service the interrupt. Classification of the interrupts of 8085 processor. The interrupts of 8085 processor can be classified in three different ways. One is hardware and software interrupts, the second one is maskable and non-maskable interrupts, and the third one is vectored and non-vectored interrupts. So now let us see about these classification in detail. The first classification is hardware and software interrupts. The device which interrupt through the hardware pins of 8085 processor, they are called as hardware interrupts. There are 5 hardware interrupts in 8085 processor. As we know, TRAP, RST 7.5, RST 5.5, RST 6.5 and INTR, out of which TRAP has the highest priority and INTR has the lowest priority. The software interrupts are nothing but they are software instructions. They are the commands given to the processor through a program. There are 8 software interrupts starting from RST 0, 1, 2, 3 up to 7. So there are 8 software interrupts in 8085 processor. This diagram shows the hardware interrupt structure of 8085. In this diagram we can see the 5 hardware interrupts of 8085 microprocessor, and in the top we can see RST 7.5, which is an edge triggered interrupt. The second one is RST 6.5, which is a level triggered interrupt. The next one is RST 5.5, which is also a level triggered interrupt. Then followed by TRAP. TRAP is an edge triggered interrupt. Finally INTR, it is a level triggered interrupt. So finally we can see the vector addresses generated by each interrupt. So we will see about this vector address in the next section. The other way in which 8085 interrupts can be classified is maskable and non-maskable interrupt. Maskable interrupts are nothing but the interrupts that can be disabled by the microprocessor. So these interrupts may be either edge or level triggered. The hardware interrupts RST 7.5, 6.5 and RST 5.5 INTR are maskable interrupts. Non-maskable interrupt is nothing but the interrupts that cannot be disabled by the microprocessor. They can also be edge or level triggered. The only non-maskable hardware interrupt is trap, and all the software interrupts are non-maskable interrupts. The next classification is vectored and non-vectored interrupts. The vectored interrupts are those when accepted by the processor automatically jumps to a specific vector address. If it jumps to a specific vector address, then it is called as vectored interrupt. The hardware interrupts except INTR are vectored interrupts. They have specific vector address that is shown here. The vector address of trap is 24, RST 5.5 is 2C, and RST 6.5 is 34, and RST 7.5 is 3C. Since they have specific vector address, they come under vectored interrupts. All the software interrupts of 8085 microprocessor are vectored interrupts. They have specific vector address, and that is also shown here. RST0, RST1 up to RST7, and the vector address jumps as 0008, 1018, 2028 and 3038 respectively. The non-vectored interrupts are those which do not have a specific vector address. The vector address will not be defined. So, the interrupting devices has to specify the address of the subroutine. So, the only non-vectored interrupt of 8085 microprocessor is INTR. This INTR hardware interrupt do not have any specific address. So, whenever any IO device which is interrupting through this INTR pin, it has to specify the address of the subroutine. So that's all about the interrupts of the 8085 processor. Now let us see the timing diagram of 8085 processor. Timing diagram is nothing but the graphical representation of the operations that is taking place inside the processor. So this execution is represented in the form of T states. Some of the terms to be remembered to draw the timing diagram of 8085 are instruction cycle, machine cycle and T states. Instruction cycle is the total time required to execute a complete instruction. So that is instruction cycle. Machine cycle is nothing but the time required to access the memory or the output devices, input-output devices. Then T state. A T state is nothing but one clock period. One clock period is nothing but which has a rising edge, a level edge and a falling edge. The machine cycles and instruction cycles of 8085 processor requires one or more T states. Now let us see the machine cycles of 8085 processor in detail and how to draw the timing diagram of those machine cycles. There are 7 machine cycles in 8085 microprocessors, namely opcode fetch machine cycle, memory read machine cycle, memory write machine cycle, IO read machine cycle, IO write machine cycle, interrupt acknowledge machine cycle and bus idle machine cycle. This opcode fetch machine cycle requires 4 T states. The memory read, memory write, IO read and IO write machine cycles require 3 T states. Interrupt acknowledge machine cycle requires either 12 T states or 18 T states depending upon the instruction through which the interrupt is accepted, and the bus idle machine cycle requires 2 T states. Let us see the timing diagram of these machine cycles in the following sections. This is the timing diagram of opcode fetch machine cycle with 4 T states. The diagram shows 4 clock pulses which is considered as T1, T2, T3 and T4. When ALE is high, AD0 to AD7 pins act as lower order address pins, and this A8 to A15 always carries higher order address pins. When ALE becomes low, automatically this AD0 to AD7 changes to D0 to D7 and it holds the opcode from the memory. During this time, the status pins will be IO by M bar equal to 0 and S0 S1 will be equal to 1. Since this is a read operation, the read bar pin is used and the read bar pin is made low during T2 and T3 whenever the processor performs read operation. So this is the timing diagram of opcode fetch machine cycle. The next machine cycle is the memory read machine cycle, which requires 3 T states. This machine cycle is similar to opcode fetch machine cycle since both the opcode and the data is to be read only from the memory. So here again during T1 ALE is made high to make this AD0 to AD7 to pin to operate as A0 to A7 and A8 to A15 always carries the higher order address, and when ALE signal goes low, AD0 to AD7 pin will act as D0 to D7 pin and it will fetch the data from memory. So during this time IO by M bar S1 S0 will be equal to 0 1 0. Here also read bar pin is used because it is read operation. This read bar pin is made low during T2 and T3 whenever the data is read from the memory. The next one is memory write machine cycle. So here we need write operation. As usual, the ALE pin goes high to make AD0 to AD7 pins to operate as address pins and it becomes low during T2 and T3 to operate this AD0 to AD7 pins as data pins. So for write operation S0 S1 is equal to 0 1, and since this is communication with memory, IO by M bar is equal to 0. So instead of read bar pin, here we use write bar pin because we are doing write operation. So this write bar pin will be made low during T2 and T3, that is whenever the data is fetched from CPU. Now coming to the IO read machine cycle of 8085 processor. Since then we have been seeing about the memory related operation. Now this is IO related operation. So IO by M bar is equal to 1 here. The operations performed by ALE, A8 to A15, AD0 to AD7 are as usual like memory operation, and here it is read machine cycle. So we are using read bar pin which is made low during T2 and T3, and for read operation as we know S0 S1 will be equal to 1 0. The next machine cycle of 8085 processor is IO write machine cycle, which also requires 3 T states. Since this is IO related operation, IO by M bar is equal to 1, and since it is write operation, S0 S1 is equal to 0 1. So when you see the diagram, again this ALE is made high to make AD0 to A7 pin to act as address pins, and it is made low during T2 and T3 so that AD0 to AD7 pins acts as data pins. A8 to A15 they always carry the higher order address. Here IO by M bar S1 S0 is equal to 1 0 1, and here write bar pin is used because this is write operation, and this write bar pin is made low during T2 and T3 whenever write operation is performed by D0 to D7 pin. The interrupt acknowledge cycle always accompanies with the interrupt instructions. So the timing diagram of the interrupt acknowledge pin depends upon the instruction along with which interrupt is generated, and the bus idle machine cycle is nothing but a straight line. So no need to explain about the bus idle machine cycle. So coming to the conclusion, 8085 is an 8-bit processor and it is the first accepted processor. We have seen about the pin configuration of 8085 processor, architecture of 8085 processor, interrupts of 8085 processor, and how to draw the timing diagram of the machine cycles of 8085 microprocessor. I think this video would have helped you in understanding the basic concepts of microprocessor, especially 8085 microprocessor, and thanks for watching this video. Thank you once again.